Okay, we'll do a dependent samples t-test example. The general idea is the same as what we did with the single samples t-test. So here's the formula. Again, it might be slightly different from the formula you've been seeing, but all the steps will remain the same. And here's where you find everything. So I'm using the nomenclature of D instead of like X bar or mu. The reason why is because I'm going to let D stand for difference here. So the primary quality of these dependent samples t-test is that we are examining if the difference between two measurements from a single group are different from each other. Or in other words, is the difference between the two time points greater than 0? And that's what's going on in the numerator. So everything is really done in regards to those difference scores, the difference between time 1 and time 2. So we're getting the mean difference between time 1 and time 2. And when we calculate standard deviation, as you see in the denominator, when we calculate standard deviation, we're calculating the standard deviation of the different scores. And so this will be a little more evident as we move forward in an example problem. So let's say that a professor wants to know if students scored significantly higher on the second exam compared to their first exam. So this is a classic dependent samples t-test idea because you have one group of students, the same group, and here I've listed them, just made up names to show that there is, that there is one sample, these students here, but they have two time points or two measurements, exam 1 and exam 2. So this is the key component of a dependent samples t-test. So what we have here is a one-tailed test. We have a one-tailed test because we notice that the wording, we see that the professor wants to know if the students score higher on exam 2 as compared to exam 1. So again, direction matters because we see that within the word problem. We want to know if exam 2 scores are higher than exam 1. And because I want to know if exam 2 produces scores that are higher, significantly higher than exam 1, but I have this one sample, I'm going to get the differences between these time points. So I'm going to subtract exam 1 from exam 2 rather than doing it the other way around. Now, I'm only doing that just so it's clear as far as the example and the work. It's really not going to make a difference whether you do exam 1 minus exam 2 versus exam 2 minus exam 1. So do not get hung up on the order. It really does not matter what you subtract from what when you're doing these dependent samples t-test. All that matters is that you're producing some sort of different score. So it won't affect the final outcome. But what I'm going to do is I'm going to change my pen color here. I'm going to write out the exam 2 scores. And from here on out, I'll probably be referring to that as just X2. But I don't think it'll come back up, so we'll just write those scores out. And then the exam 1 scores. So again, I'm going to do exam 2 minus exam 1, and that'll produce 2 minus 1, or what I'm going to call our difference scores. And when I subtract exam 1 from exam 2, here are the different scores that I get. Again, here, wrote that incorrectly. So these different scores are what pretty much everything else is going to work off of. So your very first step with the dependent samples t-test is to create these different scores. So I have pretty much I can get the average of these different scores simply by getting the mean of these differences. And that would be 4.75. So the average difference between exam 2 and exam 1 is 4.75 points. So now we need to get the standard deviation of these differences. So just like you did with variance and then finally subsequently standard deviation, it's the same process. Just instead of x minus x bar, we're doing d minus d bar. So my differences subtracting the mean differences. So to set that up, I'm just going to walk through it step by step like we have been. And again, if I were to add those up, I would get 0. That's useless to me. What I want then is d minus d squared. So again, it's the same formula that we have been doing for variance. But this time, instead of x and x bar, I'm just using d and d bar. So when I square these differences, I get these values. So now I want to add them up. So the variance of my differences, so that D is just going to stand for differences. So N here is going to equal 4 because that's the number of people I have. Now I had 2 measurements per person, but the degrees of freedom here, the N minus 1, that's all based off of your sample size, the number of people, not the number of, say, observations that you have. So that would further reduce 36.25. And again, we need the standard deviation here. So that's going to be the square root of the variance. And that would be 6.02. So now we have everything we need. So T here is going to be our D bar, or in other words, our mean differences, minus 0, because again, we just want to know, are the mean differences greater than 0? By saying are the mean differences greater than 0, we're saying there is some difference between the time points. And again, we're specifically interested in if exam 2 is greater than exam 1 scores. So we just calculated the standard deviation of the differences. And we know that our N is 4. Again, the number of people we have, not the number of observations. So this will further reduce. So that is our T value. So we do like we did before here. And what we are looking for is one-tailed, because we wanted to know if we were greater than. And we're going to go with the 0.05 significance level. So we're looking at this particular column. And then our DF, once more, is going to be N minus 1, 4 minus 1, or 3. So where do those two meet? Oops. 2.353. So we have our critical value for T, and we see that there's that critical value. The obtained T that we had, 1.58, is smaller than the critical value. So we failed to reject the null hypothesis, and here's how we'd write that out. T 3 degrees of freedom equals 1.58. P is greater than 0.05.